So basically, we just have one topic remaining to be discussed in the course, and that's Brillouin scattering, or more specifically, stimulated Brillouin scattering. Or SBS, this one. Okay, so last couple of classes we discussed Raman scattering, where basically we saw that how optical waves interact with the high frequency optical phonons in the medium, right? And that leads to Stokes and anti-Stokes scattering, and how the Stokes gets amplified and anti-Stokes get attenuated, etc. So we'll see similar effects happening here, but now the optical waves are interacting with low frequency phonons, so-called acoustic phonons, or basically sound waves in the medium. Okay. So consider a general sort of setup. So let's say you have some medium, okay, and let's say some sound waves are set up in this medium, right? So either you excite it sort of separately, or we'll see in the stimulated case that the optical fields themselves excite this acoustic wave or sound wave, right? So you have pressure or density variations, right? So let's say these bars denote like regions of high density, then you have regions of low density in between, and this sort of density wave is propagating, right? It's basically a sound. That's how sound propagates in any medium, right? So some sound wave is propagating here. Okay. So just like any wave, even for a sound wave, you can define like a wavelength, right, or a wave vector, and also a frequency, right? So, so for example, so for this sound wave, let's define a wave vector Q, or let's say QB for Brillouin, right? So this is the wave vector, and omega B is the frequency of the sound wave. Okay, so basically, just like any other wave. So let's say you take a particular location in the medium, right, and you see with time what is the how is the density fluctuating, right? So that will go as some e to the I omega bt, right? So that's the frequency, and then with respect to space, if you look at sort of what is the spacing between the maxima of the two, the maxima of the density variations, then that's some wavelength. Inverse of that is some wave vector, right? So, right. So, yeah, these are, I guess, obvious quantities. So now let's say we incident some optical wave, right? In general, it could be at some angle to this propagating sound wave. Okay. So let's say this angle. So with respect to the vertical, let's say this is theta by 2 for some, right? And due to the sort of refractive, so the density variations here act as some sort of grating, right? So regions of high and low density, you can think of it something like regions of high and low refractive index, right? So they scatter my input field into some other, just like a grating, right? So basically we call this angle of deflection. So this is the direction of the input wave. So this is the input wave, and then the direction, the angle by which it is scattered is called theta. right? That's why this is theta by 2, because theta is the angle between the scattered wave and the incident wave. Okay, so this is input and this is scattered. Okay, so typically we call the input again as the pump wave. So again, this has wave vector, let's say Kp, and frequency omega p. And then the scattered wave, let's say, has wave vector Ks and frequency omega s. Okay. So for this process, right, it's basically the pump photon scattering of these acoustic phonons to give photons at slightly shifted frequency and wavelength. So that's why this is an inelastic scattering process. So, like for any other process, you have to satisfy energy and momentum conservation, right? So, energy conservation would mean that this omega s is omega p minus this frequency of the sound wave. So basically what we are saying, what we're looking at is specifically Stokes scattering, right? So the frequency of this scattered wave is smaller than the pump wave, right? So basically what is happening, you can think of it as the pump photon interacting with the medium and then generating a acoustic phonon, right? So it gives away some of its energy to the phonon in creating the phonon, and then the rest of the energy is scattered as a photon. So that's energy conservation, right?
So this sound is traveling in a free space or a given medium.
So typically it will be in some medium, right? Of course, you have sound waves in. You can't have sound waves in vacuum, right? Because you need some material, of course, right? You need some density.
Yeah.
You need some density of atoms to be present, and then variations in that density. So, of course, yeah. So, but even air supports sound waves. But typically, for these optical interactions, typically we look at solid state media, because basically we need these frequency of the sound waves to be at least fairly high to be noticeable. Okay, like in air, typically the frequency is so low that the difference between this scatter and pump will be extremely small. You can't even sort of notice. But in solid state media, this can be big enough to notice, right? So, for example, we'll see this can be in the range of, let's say, 10 gigahertz, tens of gigahertz for solid state materials. So you can easily observe this frequency shift. Okay, because in solid state, as you know, the density is high, which means the velocity of the sound wave is higher, right, in solid compared to gas or liquid. So that also means that the frequency is higher. Okay. Right. So that's energy conservation. Again, for momentum conservation, you need the k vectors to add up. Right. So this will be, since they are in different directions, you need to write the vector rotations for Ks, the Stokes comp and the phonon. Right. So basically, okay. So how are these omegas and Ks related for the optical waves and the sound wave, right? So for the optical wave, we know that K is related to omega like this, right? Omega by c times n, where n is the refractive index of the medium, right? Or in a waveguide or something, you will have this as n effective, but this is some refractive index basically, right? So it's a linear relationship, assuming, let's say, Of course, this n is also a function of frequency. We've seen that the medium will have dispersion. But let's say around my pump and Stokes frequencies. So these two are very close together, as I said, maybe a few gigahertz apart, right? So in that range, n you can assume to be a constant, and this is a linear relationship. Okay. So basically, if I plot omega versus k, sort of a linear relationship, at least around the frequencies we are interested in, with the slope giving me the speed of light, right? Slope is c over n, which is the speed of light in the medium. Okay. Similarly, for the sound wave in the medium, right, I can draw a relationship between the frequency omega and the wave vector q. Okay, so turns out for these sound waves, acoustic phonons, again the relationship is linear. And of course, you can guess now the slope is basically just like that. The slope is basically the speed of the sound. Right? So this slope is some v, which is the speed of sound in the medium. Right? So in other words, what we are saying, this omega b is v times qb. Right? So, of course, the only the major difference between the optical and the acoustic wave is the speed, right? So, of course, this c is 3 times 10 to the 8, n is in the range of, let's say, 1 to 3 in that range. Right? So that's 10 to the 8 meters per second. But v for the sound wave here is typically orders of magnitude lower, right? So this is 10 to the 8. Whereas this v, so in air, you know, it's about like 300 meters per second or something. In solids, it becomes higher, but still it's quite low. So for example, it's usually 10 to the 3, like few kilometers per second in solid state. So you can see it's almost like 5 orders of magnitude difference. In other words, if I draw it on the same scale, right? So if I draw both of these curves on the same scale, the acoustic wave actually looks like this. The dispersion graph for the acoustic wave is, I mean, even this is exaggerated. It almost looks flat, right? So this is omega versus q. So this slope is much higher than the acoustic wave slope, right? And what is this scattering doing, right? So I pick a point, some frequency, right, omega s, corresponding to ks, and then I want to scatter it to, let's say, omega p, which is slightly higher, given by this frequency, right? And then so the difference in the wave vector that I need to provide is this much. But you can see that if I add, so for starting from here, if I add any frequency proportional to the acoustic phonon, it will have slope like this. So for this much frequency, I'll add actually much bigger wave vector. Is that clear? So in other words, what it's saying is that actually it's difficult to find a phonon with the right frequency and wave vector such that both these conditions are satisfied, right? This is for both waves in the same direction, right? So typically, like for this case, right? So here what we are considering is a longitudinal sound wave, right? where basically the sound wave is sort of propagating, or at least has a component in the direction of the optical wave propagation. Okay, so in that case, you can't satisfy these conditions basically just from the graph you can see, right? But what you can do is scatter sorry. In the backward direction. Okay, so now let me draw this dispersion diagram. So one curve will be for the forward propagating wave. Okay, and then I can draw a dispersion diagram for a backward propagating wave.
So the whole blackboard,
Yeah.
so the end sides of the blackboard are not visible totally. Yeah.
Let's see. No, what changed actually? Is this not visible?
Yeah, that is visible, sir, now.
Okay. This is also visible?
Yes, sir.
Okay. Yeah. So, right. So this is the forward. So if I call it this Z, so this is the wave propagating plus Z, and this is wave propagating in minus Z, right? So it has negative velocity. And now what I can do is, so let's say if I take the pump traveling forwards, let's say in the direction of the sound wave, and the Stokes traveling backwards, then I can choose omega S here. Let's say, so this is omega S, yes, right? And now if I add a phonon, right? So remember this slope is very small, it's almost flat. So now if I can add a phonon like this to go to omega P, where this is Ks, right? And this, sorry, Kp, and this difference is Q, right? And this difference is O. Okay, so this would be backward SBS, basically scattering from, yeah, like a pump propagating the forward direction to Stokes in the backward direction. So, and this forward SBS would not happen in this case, right? In certain special cases, you can actually get forward SBS also to happen in the material. Usually, how that's done is, so if I look at fiber or waveguide or something, and I'm looking at the cross section, right? And so the wave is propagating into the board. So then if you can set up some acoustic wave which is transverse, okay, so optical wave is traveling into the board, but the acoustic wave is transverse or in the plane of the board, right? So then you can see that there is no component of this wave vector Q in the direction of the optical wave. Okay, so basically what you want is a very small or almost negligible K vector to be added, which is what will be the case for this kind of interaction, right? When the acoustic wave is traveling also in the same direction, like a longitudinal acoustic wave, then basically the wave vector or the momentum added by the phonon is always very large, so you can only phase match this reverse or backward SBS. To do a forward, what you need to do is basically have the acoustic wave not travel in the same direction, but let's say transverse. That can be set up in certain conditions, again depending on the dimensions and the materials you have. Okay. But typically, in most cases, backward SBS is more easily observed, and especially in optical fibers where it was sort of first observed, and a lot of important work has been done. Okay, so now if I look at this, okay, so what is this? If I look at the magnitude of the wave vector of this sound wave or acoustic phonon, right? That has to be the magnitude of the difference in the k vectors between the pump and Stokes. Okay. So from this diagram, right? So this is Kp, this is Ks. So minus Ks will be sort of in this direction. So you can see Kp minus Ks is that, right? And what is the magnitude? Magnitude is, so this is magnitude of Kp, and this is Kp sine theta by 2, right? And this is roughly twice of that, right? Basically, magnitude of Ks and Kp are almost the same, right? So this is magnitude of Ks, which we can do very good approximation say is almost equal to magnitude of Kp, because these frequencies are very close. So the change is less than 1% or something, right? So even less than that. So this length here, I can approximate as 2 times Kp sine theta by 2, right? Which is basically this. So this is right. So basically, what you're saying is that the wave vector of the acoustic wave has to be equal to this, where theta is the angle of the scattering. Okay. Now, if I look at some waveguide or fiber, right? Basically, it's a one-dimensional propagation, right? So there is only you can either propagate forward or backward, right? In a bulk medium, of course, you can have all angles, but typically we are interested in doing this in a waveguide or fiber, right, to get stronger interaction. And in a fiber or waveguide, basically theta can only be either 0 or pi, right? So either Kp and Ks are both together forwarding in the same direction, which would be the forward SBS, or Kp and Ks are in opposite directions, which will be the backward. Okay. So basically this can only be 0 degree or 180 degree in a waveguide. Right, and again you can see for theta equal to 0, which means both pump and Stokes in the same direction. So this is basically 0. So you need Q to be basically 0, which is basically saying this, that for forward SBS, you don't want any component of the acoustic wave vector in the direction of the optical wave. Okay. And if theta is pi, 180 degree for backward SBS, then you can see that basically this Q has to have a magnitude which is twice of the wave vector of the pump, which is what you can see from here also, right? So Q is twice of Q.
Can you explain again how did get this expression Qs equals to 2 Kp mod of Kp sine of theta by 2?
So this is clear, of course, right? The magnitude of Q has to be the magnitude of the difference in Kp and Ks, right? Yes, from momentum conservation here. And also, what is Kp minus Ks? So this is Kp, right? direction of propagation of the pump, and this is Ks, the scattered wave. So minus Ks would be opposite to this, right? So this is minus Ks, right? And I just add Kp and minus Ks. So I do vector addition, I get this, right? So this is Kp minus Ks.
Okay, sir.
And what is the length of this? You can calculate from just simple trigonometry, right? So the length of this is Kp. So this is Kp sine theta by 2. This is length is Ks, but since the pump and strokes are very close in frequency, we can assume Ks is almost equal to Kp. So this is also Kp. This is also Kp sine theta by 2. So this is twice of Kp sine theta. Of course, the actual length is Kp sine theta by 2 plus Ks sine theta by 2. Right? But this is a very good approximation because these are very close. Okay, so, and as I said, so because the speed of sound is much smaller than the speed of light, you can satisfy this because the acoustic wave dispersion diagram is almost flat compared to the optical. Okay, so if you look at some typical numbers, okay, so this Q equal to twice of Kp means the omega, right? Which is the speed of sound times Qb. So omega is 2 times V times Kp, right? So the Brillouin shift is proportional to the speed of sound in the medium and also to the magnitude of the incident wave vector, or inversely proportional to the wavelength of my incident path. Right, so if I so this omega b, so that's angular frequency. If I want in units of hertz, then I need divided by 2 pi. You can see that, so k over 2 pi will be just 1 over lambda, right? So you get 2v and then n divided by lambda, where n is the refractive index, right? So kp is 2 pi by lambda times n. Okay, so the Brillouin shift in a medium depends on the speed of sound, refractive index, and inversely proportional to the incident length. So if I look at silica, like glass out of which optical fibers are made, then this V is about 6 kilometers per second. Okay, so if you take some other material, silicon or something else, this speed of sound would be different, right? It goes as a density and other material parameters. So if I use a pump wavelength of 1.5 micron, the refractive index of glass, you know, is about 1.45. Right, so if you put these numbers here, the Brillouin frequency shift you get is about 11 gigahertz. Okay, so basically the Stokes is downshifted from the pump by 11 gigahertz. So recall, for example, in the Raman scattering, the Raman shift was few terahertz, right? So the Brillouin frequency is much smaller than the Raman frequency. Again, that comes from basically the nature of the process. Here you are scattering of low frequency acoustic phonons, whereas in Raman you are scattering of high frequency optical phonons, right? But because now this frequency shift lies in sort of the RF microwave region, right? Few gigahertz or tens of gigahertz. you can sort of use this for RF microwave signal processing using photonics. Okay? So that's a big field in itself, using SBS for microwave photonic signal processing. Okay? So let's focus on this backward SBS, okay, which is basically, I guess, the most popular way of doing SBS. And we'll try to derive again sort of like an effective susceptibility like we did for Raman scattering, right? And then from that, like coupled amplitude equations, and see how, for example, the Stokes wave is affected due to the pump wave, etc. Okay, so again, our setup is, so let's say we have some waveguide here, right? We launch a pump, let's say in the forward direction. So this has frequency omega p, wave vector kp, right? And let's consider some sound wave in the medium, right? So basically these are density variations, right? So there is some density rho, which is a function of the position and time. Okay, so let's call this forward direction z, right? And due to the sort of Brillouin interaction, we get a backward propagating Stokes of frequency omega s. Okay, so let's consider all of these waves to be present in the medium. So typically, let's say the pump is very strong, and the Stokes is a weak wave. Okay, so basically these are, so if you plot this row of Z, it has periodic peaks and valleys, right? And it's propagating at some speed. That's basically the sound wave, right? So it has, again, wave vector q and frequency omega. Okay, so basically in SBS, what happens is that so there is a phenomenon called electrostriction. So basically, so consider these two optical waves in the medium, pump and Stokes. Okay, so they beat together, right, to give you sort of a electric field intensity, right, which is periodic, whose frequency is, the beat frequency is the difference in the frequencies, right, and it's sort of a moving grating, which is whose wavelength will be the difference, again given by the difference in the wave vectors. Okay? So there will be some optical intensity profile, right, which is given because of the interference of these two waves, and that optical intensity profile basically causes density variations due to this phenomenon of electrorestriction. Okay. So electrorestriction is basically, so in a medium, if you have regions of high intensity and low intensity, that causes density variations corresponding to the intensity, right? Basically, so some in the regions of, you can imagine sort of in the regions of high intensity, atoms are getting pulled towards each other. In the regions of low density, sort of, right? So here, sort of atoms are getting pulled together, and in the low region, they are getting pulled apart, right? Or vice versa. So some kind of gradient forces on the atoms, which sort of stretches their bonds. Okay. So this density variation is set up by this electrorestriction phenomenon, right? Which is basically, if you have a varying optical or electromagnetic intensity in the medium, that gives rise to a density variation. Okay, so of course this density variation will be very, very small, right? So you have some mean density of the medium, and this will be sort of fluctuation on top of that, right? Some regions of high and small density, but the amplitude of this compared to the average density will be very, very small, right? Because so this phenomenon is actually very weak, right? But what we'll see is that even for when the density variation is extremely small, basically if this process happens coherently over a long length, then the scattering can be extremely efficient, and you can even, for example, transfer 100% of the power from the controller. Okay, so again we'll start the analysis like, I guess, what we did for the Raman scattering also, right? So the optical field, we consider the electric field that will have the pump and the Stokes, right? And again, I take the pump, it's an amplitude AP, which becomes a function of Z, right? And wave vector KP, frequency omega p, traveling in the plus Z direction. Stokes has amplitude AS, is traveling in the minus Z direction, right? So the minus K is set there. Of course, to make it real, to add the complex functions, right? And then you can similarly write the acoustic or the density variation, right, in the medium, which is rho, again, function of space and time. You can write it as an average density, so rho naught, which, for example, is the density of the medium without these optical waves and without the SBS interaction, and plus the change in this density, right? So this delta rho in magnitude will be very small compared to rho naught. That's what I was saying. Typically, like say, it will be like, I don't know, 10 to the minus 8 or something. But even then, you'll see that the effect will be very strong over when it builds up over the length. Right, and now this density variation also is like a wave, right, with wave vector q and omega. So we can also write this density variation as so this delta rho z of t can write it as some amplitude times, again, this propagating wave with wave vector q and frequency omega. Okay, so this is this sound wave. Right, and omega over q is the sound velocity. Right, and so for this backward case, so q is basically kp plus ks, or basically twice of kp, right? And this omega is omega p minus omega s. Okay, so just like Maxwell's equations for propagation of electromagnetic waves in the medium, right? There is also propagation equations for sort of these density waves or acoustic waves in the medium. Okay, so there is an acoustic wave equation which this rho follows, right? Which we can write as, so that comes from like solid mechanics or solid state physics, right? So okay, so we can write an acoustic wave equation. Okay, so I mean, it almost looks like, for example, the simple harmonic oscillator equation that we wrote for example, the optical phonons, right? Right, so you have some acceleration kind of term, damping term, right? And this is like the natural frequency term and some driving term. Okay. So let's not worry about the details of each of these terms, but sort of it's a wave equation for the density. Okay. So v here is the speed of sound. Okay. This gamma prime here is some damping parameter. So basically, if you set up a wave, it won't propagate forever, right? It has some decay time, so that's some damping parameter here. You can think of it's related to, again, like the lifetime of the acoustic phonon. So v is the speed of sound. Right, and this driving term on the right hand side, so this divergence of some quantity, so this F is force per unit volume. Okay, which is written as the gradient of some pressure term. Right, so pressure is force per unit area, you know. So if you take a gradient, that's force per unit volume. Okay, and this pressure is basically the electrostrictive pressure. Basically, this is what is giving rise to, this is like a pressure on the atoms, right? Due to the optical intensity. Okay? So this is what gives rise to the density variations due to a variation of optical intensity in the medium. Okay, so this electrostrictive pressure, EST, is written as something which is proportional to the energy, the intensity of the energy density in the medium. Right, so E square, or because we have rapidly varying quantities, we take sort of time average over optical cycles. So average of E square. So half epsilon naught E square, that looks like the energy density, right? Or equivalently like intensity. So it's proportional to that with a proportionality constant, this gamma E. Okay. This gamma E is basically called the electrostrictive constant. Okay, so that's a material property. Right, so for a given optical intensity, how much pressure is induced is given by this gamma. Right, so this is what will give me the Brillouin nonlinearity. Right, so a higher gamma E means I have a stronger Brillouin interaction. Right, so what is this gamma E? Specifically, it's basically how the susceptibility right, so this tie is basically the usual electric susceptibility, right, which gives basically like the refractive index, right? So how that susceptibility changes with a change in density. Okay, that's what this electrostrictive pressure is. So if the susceptibility changes by a larger amount for the same change in the density, then I have a larger gap. Okay, and you can see that a larger refractive index variation will give me larger scattering of the pump to the stores, right? So, to give you some idea of some numbers, so this rho naught, the average density for glass. So if I look at silica glass again, this rho naught is about 2000 kg per meter cube. And this gamma E, the electrostrictive constant, is about 0.9. Okay, so gamma is unitless, you can see. Right, the rows cancel out, susceptibility is unitless. This gamma is also unitless. So in silica, it's value of 0.9. Okay. So higher the value of this gamma E, stronger is the Brillouin interaction. Okay, so to erase some things here. Right, so okay, so this electrostrictive pressure, the gradient of that gives me the force. So okay, so del dot F is the driving term. So del dot F, if I take del dot of this, I get del square, right? So I get del square of this pressure, and for this pressure, I can put in this expression here. right? And then the only term which is spatially dependent is the E square term, right? So del square of, I'll get this average of E square. And so the electric field, if you remember, we wrote, so that has the pump and Stokes, right? AP e to the I kp z minus omega pt plus as e to the I minus ks z minus omega st. So that's E, right? Plus complex conjugate. If I square that, you can see I get a term goes as AP AS conjugate and has right. So recall that, so E is AP e to the I AP z minus omega t plus AS I right. So if I do E square this whole thing, I'm looking for, again, recall that I wrote the density wave as something which had this kind of variation, e to the I q z minus omega t, right? So basically I want to look for a driving term which has the same form, right? This, a driving term of this form will give me a density variation of this form, right? So how will I get a driving term of this form, right? Where I have E with terms like that. So Q, again recall Q was Kp plus Ks and omega was omega p minus omega s, right? So when I square this, the product of this AP term with the conjugate of this AS term will go as e to the I kpz, and here I'll get e to the I ksz, right? So AP AS conjugate and then e to the I kp plus ksz, which is basically qz, and then the time variation would be e to the minus I omega p minus omega s t, which is omega, right? And again we have a complex conjugate of that. Right, so you can see this pressure term or the driving term goes as APAS conjugate. Right, so this, recall that this looks very similar to the Raman scattering case where we were looking at this amplitude of the vibrations, right, of the atomic or molecular positions, and there also we saw that those vibrations were driven as like by this term, APAS. Right? So similar here, like the density wave is driven by terms which are given like APAS conjugate. Okay. Okay, I hope this is clear. Okay. And now if you want to take del square of this term, you can see that the only sort of main spatial dependence here is in the exponential here, right, qz. So I mean, in principle, AP and AS are also become functions of z, right, due to the Brillouin interaction. But let's assume that the variation is very slow. Again, something like the slowly varying envelope kind of approximation. So the derivatives of A versus so d del square A by del z square, etc. Let's neglect that. So the only terms which will come is this derivative of so e to the iqz. When we take derivative, this iq will come outside. the only variation is the z direction, and that too we just take the exponential. We sort of assume that these amplitudes are slowly varying. So then this term I can approximate as, so del dot f. So I just take iq square outside here. Okay, so this driving term here goes as some constants. Of course, it has the electrostatic constant, and then APAS conjugate, so the amplitudes of the pump and stop, right? And it has a spatial temporal dependence, which is goes at qz minus omega t, which is what will drive a density wave of the same nature. Okay, so again, so now this is like a wave equation with a driving term, where the driving term looks like this, right? And again, this is like almost like a simple harmonic oscillator kind of equation. So we take the solution of the same form, which we already wrote down, right? So the solution for rho we take as rho naught, some constant, plus delta rho e to the I qz minus 1.
So we have taken the application slowly varying. So we have also generated the first order derivative.
Yeah. Yeah. So basically, we are saying that all the rest of the terms compared to the q square times this term is much smaller, right?
Usually, sir, we second order derivatives, first order derivatives.
Yeah. So you're right. So recall. So when we write the the optical wave equation, right? There, for example, when we derive the canonical propagation equation, we keep the first order term to get the equation, right? So here, sort of, what we are looking at is the acoustic wave equation, right? And the driving term for the acoustic wave equation. So basically, what we are saying is that over one sort of over one wavelength of the density wave, right? This APAs don't change much, right? So if you keep the first order term, then you'll have terms like dAp by dz, right? But we are saying that so we are looking at this acoustic wave equation. So over and we're seeing how this density wave is changing. And so basically we are saying that for the density wave, the driving term, right? So this term is much bigger than the next term, which you are saying which will have dAp by dz, right? Because dAp by dz over, let's say, one wavelength of the density wave is not changing much at all. Okay, so it looks locally. If you look, then another way of saying is that sort of what we are doing is we are breaking this whole medium up into sort of segments and looking at the density wave in each segment, right? And for this segment, we are saying, okay, APAS is some constant value in this segment. We solve this equation, right? And then we go to the next segment, AP and AS, of course, will be slightly different because they changed now. Again, solve this equation, etc. Right? So this will be like AP of Z, AS of Z. Here. Okay, I hope that's clear. So you're right. I mean, it's an approximation, right? We are neglecting the, but that approximation is good if, right? So this density wave is changing here, and if APAs don't change much over, let's say, wavelength scales of the acoustic wave, then it's a good approach. Okay.
Okay, sir.
Yeah. So it's sort of like a, and it's not the usual slowly varying envelope, right? Here we are looking sort of at the acoustic wave and how that changes, and it's like a slowly varying envelope for that case. Okay, so okay, so we have this. Okay, so basically here on the right hand side we have this term, so something going as e to the I qz minus omega t. So we look for again solutions rho naught plus right. So if we plug in this solution into this equation, then we'll get exponential terms on both sides which are the same, right? So we can just look at the amplitudes on both sides in front of the exponential terms. So here, so first term here, I have a double derivative with respect to time. So I'll get omega square, right? I have the I omega t here, so I'll get omega square because of that double derivative of time. So I'll get minus omega square times delta rho. In second term, I have single derivative, so I'll get one term of get I omega. And then I have a del square here of right. I also have a del square here. So the only dependence is with respect to z. So again, del square basically is just the only term is d by dz square, and when I operate this on that, I get q square. So we have I e to the I q z, right? Right. So I get a factor of q square also here. So minus q square times delta rho. And then again here I have a del square again, so I get q square again here. right? And on the right hand side, I have this driving term. Okay, so that's the equation I get for delta rho, which is the amplitude of the density fluctuation or density wave. So here I'm getting a term like Q times V, right? We know that Q times V is basically the frequency, right? So this is the wave, acoustic wave vector. This is the acoustic speed of the acoustic wave. That gives me acoustic frequency. So let me call this omega B, which is the Brillouin frequency. And then here I have a term of Q square times this gamma prime. So this Q square times gamma prime is defined as gamma B, which we'll see is basically the Brillouin line width. Right. So just like in the Raman scattering case, we had a Raman shift and a Raman line width. Right. Similarly, here we have a Brillouin frequency shift, and then we have a line width to the Brillouin gain shape. That is this omega gamma B. Okay. So this gamma B is basically inverse of the phonon lifetime. So how long the acoustic phonon stays in the medium before decaying? That's inverse of that is the Brillouin line width. Okay, so in terms of these parameters, basically I can write the left hand side like this. Okay, so from here I get the expression for this amplitude of the density variation. Okay, and now this expression looks very similar again to, for example, the amplitude of this lattice vibration that we were computing for the Raman scattering case, right? So it goes as APAS conjugate, and then the constant proportionality here is gamma E, which is the electrorestrictive constant. And then in the denominator, I have a very similar term with respect to frequency here, right? In the Raman scattering case also I got something very similar like this, right? So this is what will give me this Brillouin, Lorentzian shape, like for the Stokes gain, for example. So very similar to the Raman case, except just the constants are different because the fundamental interaction here is electrorestriction, so those constants show up. Whereas in that case, it was the Raman coupling. Right? Okay, so now we have an expression for the density wave. And we know that basically this electrorestriction is that a variation in density causes a change in the susceptibility. Right, so remember this gamma E was del chi by del rho. Right, so a change in density will cause a change in the susceptibility. And a change in the susceptibility means change in the polarization, right? So P, the polarization induced in the medium, is epsilon naught chi E. The change in chi will give me a change in P, right? Which I can define like a nonlinear polarization. Okay. Similar to what again we did in the Raman case. Yeah, so the polarization induced in the medium P will epsilon naught chi times E. Right, so now this chi is sort of the usual linear susceptibility of the material plus the change due to this change in the density of the material, right? And so this delta chi I can write as del chi by del rho times delta rho. Okay? And so remember this gamma E was rho times del chi by del rho. So you can write this as gamma E by rho naught times delta rho. Okay. So again, I can write this as a linear part plus a nonlinear polarization. Right, the linear will just be the sort of the bare chi1 of the material, and this will give me the nonlinear polarization. Right, so this I can write as, so this is my usual linear one, which gives me the material refractive index, etc. Right, so see, both of these are functions of right, delta rho and E are functions of Z and T. So this is also. Right, and so this delta rho Z comma T is this delta rho times, right, so this is this delta rho times e to the I qz minus omega t, and this E is, remember, the pump from Stokes. Right, so you can see that this nonlinear polarization here will have terms going as at the pump frequency and the Stokes frequency. Right, so I have a product of these terms here. So you can get terms at like this omega plus omega p, or negative of that, or this omega plus omega s, right? And recall omega was omega p minus omega s, right? So, for example, this delta rho times as term will go as, the frequency will be omega s plus omega, which is omega p, right? So that will give me a term going as at the pump frequency, right? Similarly for the Stokes frequency, so like the conjugate of this times AP, so that will go as omega p minus omega, that will go at the Stokes frequency. Okay, so yeah, explicitly, so I can write, for example, the nonlinear polarization at the pump frequency right? So again, that will come from the product of delta rho and AS, right? That will have a frequency omega plus omega s, which is omega p. And then the spatial dependence of that will be this q plus or q minus ks, and q, remember, was kp plus ks. So q minus ks will be kp. Right. Similarly, the nonlinear polarization at the Stokes, right, will come from the product of delta rho conjugate. So the conjugate of this will have e to the I omega t multiplied by the pump e to the minus I p omega t. So that frequency will go as omega p minus omega, which is omega s. Right, and again the spatial dependence will be kp minus q, which will be minus ks. Okay, so you can see that the pump is driven by a nonlinear polarization whose spatial variation is like the pump wave, e to the I kpz. Similarly, the Stokes is driven by the nonlinear polarization whose spatial variation is also like the Stokes wave, e to the minus I kz, because the Stokes is traveling in the minus. So now you can see, so the expression for delta rho we have here. Delta rho is goes as AP times AS conjugate. So in this term here, I have delta rho times AS, right? So this will be proportional to, I have AP AS conjugate times AS. So this will go as mod AS square AP. Whereas this term will go as the conjugate of delta rho. So that's AP conjugate AS times AP. So this goes as mod AP square AS. Right? Again, so these should be familiar terms. Right? So I have a nonlinear polarization which goes as mod AP square AS. So this looks something like, first of all, it's a third order nonlinearity because it has three fields here, right? Similarly, so it's a third order nonlinearity, effectively third order nonlinearity, and it looks like again this cross phase modulation term, or the term like we got for Raman scatter, right? So mod AP square AS, the Stokes tool is mod AP square AS, the COM tool is mod AP square. Right, so the constants of proportionality here I can define as its effective chi3, right? Because if I write third order nonlinearity, third order polarization as epsilon naught chi3 times the products of three fields. Right, and E1, E2, E3. Right, so basically the constant here I can define as a effective chi3. Same like what we did for the Raman case. Okay, so specifically, you remember we can write this as 6 to take into account the number of permutations. Chi3 Brillouin. Right, so this is at omega p due to omega s minus omega s omega p. Right, similarly here I can write it as Chi3 Brillouin omega s due to omega p minus omega p omega s times mod AP square as. Okay, so basically from there I can define the chi3 due to Brillouin. So for example, at the Stokes frequency, which is omega p minus omega, okay, I get basically a very similar or basically the same expression as I got for the Raman susceptibility, except these constants are different because here we are looking at electrorestriction, but this factor, for example, is the same, except instead of the Raman frequency, you have the Brillouin frequency in the Brillouin line. Okay, and again, just like the Raman case, this has both real and imaginary parts, right? So basically, this is similar to the Raman case. Just instead of omega r, you have omega b, and sort of this Raman language, you have Newman language, and these constants are different, of course. And again, has both real and imaginary parts. So just like the Raman case, the imaginary part will give me gain or loss, and the real part will give me a refractive index change. right? So if you recall, just like the Raman case, we can plot this. We can separate this into the real and imaginary parts and plot each of them versus frequency. And we get exactly, the shape is exactly what we got for the Raman case, except the frequencies are different. Okay, so in the Raman case, basically the shift was, we saw like few terahertz, right? And this line width we saw was, let's say, like hundreds of or 100 gigahertz or maybe even larger. In the Brillouin case, this is like tens of gigahertz, and the line width is typically let's say tens or hundreds of megahertz. Okay, so you go sort of 3 orders of magnitude down, both in the frequency shift and the length. Okay, so now if you plot this right 3, so again in the middle we have the pump frequency. Right, and here we have omega. So on the low frequencies, so if you plot, for example, the imaginary part, it looks like that. Right, so this is the shift omega b. Right, so this is the imaginary part of chi3 Brillouin. So on the low frequency side, so this is Stokes. High frequencies are anti-Stokes, so you get loss for anti-Stokes and gain for Stokes. Okay, a negative value for the imaginary part leads to gain. Again, when you write the coupled propagation equation, and positive part leads to loss. And if you plot the real part, again, it sort of looks like the derivative of this. So this is the real part. Right, so you get a very fast refractive index change around the Stokes and anti-Stokes wavelength. Right. So again, recall that so dn by d omega. So this line width here is the Brillouin line width gamma b. Right. And you can see for Brillouin it's actually much narrower, right? Than even Raman, it's in the megahertz range. So this refractive index is really changing very fast because this is very narrow. Okay? And so recall again our discussion for the Raman case, where so if you have a large value of dn by d omega, that means you get a large change in the group index, which means you can delay pulses of light. Right? So Brillouin is also used for that. The real part can be used for that. So again, if you have the susceptibility, we can go to the canonical propagation equation, right? Same again, everything same as what we did before for Raman. Um, right, so once I have a nonlinear polarization, I can write the canonical propagation equations. So recall, so for the pump, it will be dAp by dz. Right. So for the Stokes, which is well, there will be sign change there. So maybe I should not. Right. So for that, and then with the Stokes. So for the Stokes, I'll have instead of minus I, I'll have plus I because it's traveling in the opposite direction. And recall that this P nonlinear at omega P went as e to the I kpz, so that we cancel this out. Similarly, this one went as e to the minus I kz, so that we cancel that one out. And we just put the expressions for this nonlinear polarization that we had derived. So you get, for example, for the pump, and for the Stokes, we get okay. So again, the Stokes goes as mod AP square Ks, and the pump goes as mod A square. If you want, like, again, you can take real and imaginary parts of this, right? So, for example, you can write this as Okay, so you have one part which goes as I times something, right? So dAp by dz is I times constant times AP, so that looks like a refractive index, right? And the other term will be, you can see i's cancel out, so that will be dAp by dz equal to something times AP, so that looks like a gain or loss. In this case, it looks like a loss for the pump because the pump is the anti-Stokes of the Stokes, right? And similarly, on this side for the Stokes, you get very similar. So the minus here comes because Stokes is propagating the minus z direction, right? So you have actually dA by minus dz. That's where this minus comes from. So anyway, again, yeah, I won't write down the whole thing, but yeah, very similar terms here. So right, again, the first term will give you some phase change, and the second term will give you gain. You can also see how the intensities vary, right? So these are exactly the same expression that we got for Raman, except just R is replaced by B, right? And this constant is different. The form is exactly the same. So I can also look at the intensity, right? So I know intensity I can write as mod A square times that, right? So di by dz would be A times dA conjugate by dz plus A conjugate dA by dz. Okay, so you can take the conjugate of this equation and then substitute here. So what you will see is that the phase change parts cancel out, and because for the intensity, of course, the intensity doesn't, it's independent of the phase, right? Because you're taking mod k square. So only the gain and loss part remains for the intensity. So you can see for the pump, you get so these constants times minus IP. Okay, and you can check for the Stokes, you get the same equation, exact same equation. Okay, so again recall these are exactly similar to what we got in the Raman case, except we had a plus there because there we sort of considered both pump and Stokes traveling in the same direction. Here they're opposite directions, so that's where we get the minus from. But you can see that, okay, so for the pump, it's traveling in the plus Z direction. So this actually means a loss for the pump, right? The pump intensity will decrease as it propagates forward in Z. Whereas for the Stokes, it's traveling in the minus Z direction, right? So equivalently, I can write this as minus di by dz equal to plus this, which means as it propagates in the minus Z direction, Is actually increases, right? So that's gain. Okay, and this G basically depends on all these electroreceptive constants here. This Brillouin gain factor G. Okay, write that G as so. It will be good exercise to go through sort of all these equations on your own and derive all these things on your own. Right? And just check all these signs, etc. Of the constants. Okay, so this G, of course, has those constants and a frequency dependence, right? So you call the frequency dependence or something like this. Right? So, and this G naught had all those electroreceptive constants, gamma E, etc. That's in G naught. So you can see that G is greater than 0 if omega is greater than 0. Right? The denominator is always positive. So G here is just proportional to omega. So if omega is positive, G is positive. That means basically Stokes, right? Because omega, recall, was omega p minus omega s. Right, so if you plot this Brillouin gain factor, as a function of this detuning omega from the pump, then if omega is positive, which means, right, so this is omega p minus omega s, which means omega s less than omega p, you get gain, G is positive. Whereas for omega s greater than omega p, or this omega negative, you get loss. G is less than 0. Right, so again, this is loss for anti-Stokes and gain for Stokes. Right, and the peak gain occurs at omega b. Omega b shift from the pump. And so this expression can be simplified for frequencies close to omega b. Remember we did this also in the Raman case, right? So around this gain resonance, so for omega close to omega b, I can approximate the numerator as that, and then the second approximation is right omega b square minus omega square as omega b plus omega, which I approximate as 2 omega b. So basically, I linearize this into a different stuff, and then you can see that this becomes like a Lorentzian, right? So this gain shape around the peak can be approximated as a Lorentzian function. With line width this gamma b. Right. So this full width or half max here is gamma b. Right, and the peak gain is this GB. Right, and this peak Brillouin gain again, if you go back to where we got this from, in terms of the material constants, it depends on so it depends on the electrostatic constant. And for a high gain, you want a large electrostatic constant. Right? It goes as square of the pump frequency, and then inversely, it's related to the density, refractive index, speed of sound, and this Brillouin line width also gives here. And typically, we usually take another factor here, which is sort of the, you can call like an overlap factor between the optical and acoustic modes. So imagine like you have a waveguide of fiber, right? So typically you have some optical mode which is propagating. Similarly, for the sound wave, you have some transverse profile which is propagating, and the overlap between the two comes here, right? So the best case would be if they perfectly overlap, the overlap factor is 1, right? But if not, then this will be less than 1. In optical fibers, typically this is very close to 1, the overlap factor. But if you get to sort of micron scale or nanoscale waveguides, then you have to worry about this overlap factor. Okay, so and so typically actually this Brillouin line width, or basically the inverse of the lifetime, that typically scales also with the frequency, like omega square. So typically this Brillouin gain is independent of pump frequency. So these cancel out. So give you some typical numbers, right? So remember this omega b, we wrote it as some omega prime times q square, right? And this q is basically just proportional to omega, right? Because q was kp, related to kp, and kp is related to omega p. So q square k is omega p square. Okay, so that's why. So yeah, so basically independent of the pump wavelength, this dB is sort of material value. Whereas I think for the Raman, if you saw, the Raman gain scaled linearly with the pump or Stokes frequency. So if you look at some typical numbers, so this GB for silica optical fibers is about 3 to 5 centimeter per gigawatt. Right, so you can see that the units for G have to be meter per watt, because yeah, you can check from here. Right? So for your typical optical fibers, it's about 3 to 5 centimeter per gigawatt. Okay. Now, if you compare this with the Raman gain, right? So so this GB, let's say about 3 centimeter per gigawatt. The Raman gain, if you recall, was much smaller. It was about 10 to the minus 2. So this is in silica. Right. So actually, turns out for optical fibers, Brillouin interaction is much stronger than Raman. And this line width again for optical fibers is about between 10 to 100 megahertz. So it's very narrow. Okay, so this is almost time. So yeah, just before we close, so we can look at what kind of amplification for the Stokes we can get, right? So from these equations, you can see that so if I take d by dz of IP minus IS, that's actually 0, right? So if I just add these two equations, this cancel out, which means IP minus IS actually remains constant, right? So what is happening? So if I plot as a function of Z, so I start with some input pump intensity, right? And that keeps decaying. And from the other end, what's happening is the Stokes is getting amplified. Right? So the pump is going like that and the Stokes is traveling like that. So this difference, IP minus IS, so this is IP and this is IS. So I send in some pump intensity and actually at the input end, I get a back reflection, right, which is the Stokes intensity. And this difference throughout the propagation length is constant. Okay, and depending on this gain value, so if I consider the pump to be much stronger than the Stokes, let's say that the conversion to Stokes I assume is small enough, then I can assume a constant pump or pump undepleted approximation, right? So then this I can just integrate with IP constant. So you can see that the intensity of the Stokes So you have to integrate starting from L up to 0 because the Stokes starts from the other end and comes to the input. Okay, so it's in terms of the input at the IS of L, right, at the other end. So it grows exponentially, the pump intensity. Right, so if I calculate a gain factor, Brillouin gain, net amplification factor, which is how much Stokes I get at the input here versus what I sent at the other end. So this is again e to the IGIPL. And I can write P over the mode area in the fiber. Right now again, so if I put typical numbers, so G, this value, if I take a pump power of about 25 milliwatt, I take a length of 1 kilometer, mode area of a typical standard telecom fiber, for example, is about 50 micron square. If you put these numbers here, you actually get this as e to the 25, which is about 10 to the 11. So that's a very, very large gain. Right? Recall, we tried to do this exercise for the Raman, and there we had numbers like 1 watt and similar length, etc. And there we only got a gain of, I don't know, like 10 or 100. But here you can see, because the Brillouin gain factor is about 2 orders of magnitude larger and it goes in the exponent here. You can see for the Brillouin, for much lower powers, like 25 milliwatts over a kilometer length, the gain is actually like 10 to the 11. Okay, which means that you actually don't need any input here. Like any small noise will get amplified a lot. Right? And so typically this is what happens in telecommunication networks. Right? You want to send some optical signal. Typically we send it over kilometers. Powers we use typically a few milliwatts. But you can see that this is a big problem. Right? What can happen is basically due to Brillouin scattering in the fiber, most of your light can get back reflected towards your transmitter itself, right, as Stokes light. So nothing actually gets to my receiver. So this is a big problem initially in optical communication networks, right? So I'm just sending one signal that I want to send from the transmitter to the receiver, which has, let's say, some data of zeros and ones. But because the Brillouin gain is so large, this sort of SBS starts from noise and then takes over, and all my pump power is converted to Stokes, and all this is I get back at my transmitter almost, let's say 50% or more of my light comes back. Okay, and nothing gets to the receiver. So this is was a big problem for optical communication networks, and we'll see how we get around this problem. So maybe we'll start with that next class.